Okay, let's get started. Wow, I have this microphone today. I feel important. I sound loud. Well, to me, probably just to me. All right, so today I'm going to talk about software reliability. And one of our topics, it's lecture 6A. We have lecture 6A, 6B, and 6C that cover reliability, security, safety, a bunch of software engineering topics related to what happens when things go wrong. And it kind of gets into the concepts of verification and validation in terms of software and software design. And it goes above and beyond like the development and what you should do in the development cycle. It actually comes and plays a lot with common sense in some ways too. And it kind of brings to light as well some things that can't be tested for. Sometimes you have an issue in software that is just there, inherent in the design of the software. Maybe it's a concept-related thing. Maybe it's a business process that changed, but the software didn't change correctly, or an unknown kind of event that occurs. And that's the example, actually, that comes forth. And I'll leave this out here so you can read through it. But briefly, just to mention the example, there was a cruise ship, had 1,509 people on it. This was back in... Actually, I think this was in the 1980s when they put in these navigation systems, these GPS systems. It's kind of like what they have in airplanes. And you know how when a pilot puts something on autopilot and they can sit and drink coffee and read a newspaper and the plane just flies itself? Well, in some cases, like cruise ships do this too. You know, in fact, you have it in your car, cruise control. So what if you put your cruise control on in your car, but there was a software glitch, let's say that, you know, when it went over a bump, it automatically increased by 5 miles per hour or something like that. Then you might actually have a problem in the future that you may not even be aware of. In fact, that's kind of like what happened with this cruise ship. But this story goes in terms of when the GPS couldn't make a good signal with the satellite, it went into an auto navigation mode. And this caused actually some people not to realize where the cruise ship was actually going to, the destination. And it basically shows you how technology, although there's no bug in the system, it had a bug inherent in the design of the way it was put together, which made it kind of unreliable. In fact, you know, most of us rely upon technology for a lot of things. If the technology fails, we never really expect it to fail. And when it fails, it's like, oh, you know, that's bad. Let's reboot the computer. But when it's like a heart monitor, or it's like a navigation system for a cruise ship, or it's an autopilot for an airplane or something, it might actually be a critical error that happens. So this particular cruise ship was setting sail, it lost a signal, it ended up going in the wrong direction. You can go ahead and read through the slide set. In fact, if you want, it's lecture 6A. If you download it, if you download the PowerPoint, so you can go through it. But long story short, the ship was steered on an autopilot mode that relied on a GPS system for global positioning. And it had a kind of a default mode. If it couldn't reach a signal, couldn't communicate with the satellites, it went into a default mode. The default mode was actually called a dead reckoning. I'm not really familiar with GPS, but the dead reckoning is supposed to be distance and direction traveled from a known point. Anyway, long story short, it went on some sort of a default route that it was trained to do, and they lost it. I mean, the cruise ship, you know, didn't end up becoming destroyed. It just landed somewhere different, and so it wasn't quite the destination they were expecting. And it was holding a lot of passengers. So the GPS failed 1 hour after leaving Bermuda, and it ended up kind of getting lost out in the sea, which could be kind of a problem, depending upon what happens. So the crew failed to see the warning signs as well. In fact, I guess the system, it's kind of like the warning signs we get in our cars, you know, the check engine, you know, or people, you know, it pops up, you go, oh yeah, it comes on all the time, and you ignore it. Or maybe some people don't even look at those things, or, you know, why do I have a red button on this computer constantly or something? So it could be an issue where people actually don't even see the warning signs and don't even see anything like that nature. But they saw it, they ignored it. So 35 hours and 600 miles later, they figured out what was going on, and it was like 17 miles away or something. But it pretty much got lost, essentially, because there was no way of locating it from the GPS. Anyway, so the lessons learned on this, and if you think about it, it's a software application, somebody's engineering project to put together this navigation for this cruise ship. And all the software worked according to plan. There were no bugs in the system. It was designed correctly. It was, a logic issue that happened. And so since the GPS software had been specified, the requirements had changed, actually. So the standalone system is part of an integrated system. Because the requirements actually kind of changed, the logic changed in terms of what the default behavior should have been for when it lost a signal, which happens all the time, actually. In fact, this is how we have software that needs to be updated occasionally, like when the date changes. From the year 2000, we had that issue that was going on. Every day we have other issues, though, that come out in software engineering. They create these situations where requirements are totally different. We see this a lot with operating systems. So we get new hardware, and the hardware is maybe faster running memory, maybe, or more hard disk space. In the old days, if you upgraded your hard drive too soon, the operating system didn't see it, and it couldn't use all that available space anyway. So unless you had the right software to work with the right hardware, and then as well as the business environment. So long story short, it causes reliability issues. Just time and existence does that. Manufacturers of autopilot systems and GPS adopted different design philosophies as well about the communication of the module changes. So design, in fact, things like technologies like infrared, and in fact we see it all the time with cellular phones, not cellular, cordless phones that work on a 2.4 gigahertz kind of thing. And everybody knows if you get a portable phone system that's wireless, and you get a wireless network, there's going to be, 9 times out of 10, there's going to be an issue. There's going to be cross with signals. So one's going to work, and then the other one's not going to work, and vice versa. So you get different frequencies, or you can get different codes to set everything, including infrared devices and stuff. So. And if someone comes through and changes the configuration or comes out with new requirements, all of a sudden we have issues as well. We see this when we have a cellular phone in our car, and every time we get a text message or the phone rings, it makes a buzz through our radio station or through our radio in-console thing, because nobody ever thought about the concept of there being interference when they installed the radio. So it wasn't grounded, or it's running on a similar frequency as our cellular service, or it's doing something that's not compatible. But car radios have been around before cell phones, so you can't blame one and not blame the other, vice versa. So also, the autopilot was not programmed to recognize valid and invalid status bits. Warnings provided by the user interface were ignored, or maybe they weren't sufficient. Maybe they weren't big enough as an alert. And actually, that's kind of an issue that's happening in cars these days with that check engine light, going back to that concept. In the old days, if the check engine light came on, you pulled over to the side of the road, because there was a serious problem with the car, because that light never came on. Now it comes on for everything. You leave the gas cap off, the check engine light comes on, everything. So now there's less significance to it. It's kind of like that old child's fable thing, crying wolf. The check engine light comes on too often, we don't trust it anymore. Maybe we should have pulled over, but we didn't because, check engine light comes on. Same thing happens with computer programs, though. And what if it's a banking application? Maybe it's an ATM machine. Maybe it's something, constantly makes errors, and we have this weird consumer trust in it. And we slide it through a couple of times, and lo and behold, it deducted it 5 times, but we only got the cash once or something. So problems like that exist, and that's what is covered under the topic of software reliability in terms of this lecture. What do we have here? The officers also in this ship example were not properly trained on the equipment. They actually didn't know what the equipment was doing. So usually, actually as a result of this autopilot issue, now you see more and more people practicing the autopilot just to make sure that just in case we need it, autopilot actually works correctly. So sometimes you might hear airplanes land on autopilot. Sometimes they take off on the autopilot. Sometimes they announce it to you as a consumer. Sometimes they don't. But occasionally they will test things just to make sure that autopilot's actually working correctly. Because it's there to make the software, to make the plane, to make the device more reliable. But it's not reliable if it doesn't work, and we don't test it till we need it. It's kind of like how people have drills, safety drills, fire drills. You know, like if we had an earthquake right now, would you know what to do? Probably not, actually. I'd be running out the door. I don't know about the rest of you. In the old days, you know, especially in the United States, as children, you know, they had a duck and cover, they called it, and you got under chairs. So they told you like where to stand, how to form a line, stuff like that. And basically, it's for reliability. It's a low-tech version of reliability, but it's all the same. As software or hardware does not, or software engineering in general, there's no difference with technology. It's the same concept. So reliability is the probability of a failure occurring in operational use. You can actually stick this in the requirement specification. Must be reliable to 99.9% accuracy. Because is anything really 100% reliable? I don't know. Even hardware is not 100% reliable. You know, there's issues like overheating, bad connection, static electricity, interference. So everything is like 98, 99%, I would say. If someone says, oh, this is 100% reliable, I don't believe it. And software is less reliable than hardware. Because, you know, you'd think it would be the opposite, because hardware's got moving parts, but software is too dependent upon outside factors and things. So there's a little bit more communication that goes on in interrelationships with other components when you talk about software. So perceived reliability depends on, and this is your perception of reliability, user behavior, sets of inputs, and the pain of a failure. If the failure pain is really high, it has to be reliable. It's kind of like people's operating systems. In the old days, people didn't like it when the whole computer shut down, you know, because, oh my God, you know, I have to go restart everything, and I lost all my data. So you can build logic into software so that if it's going to crash, you can give a warning. You probably should reboot now, or you should probably close all your programs and start over again, which is why a lot of software installs have you close everything before you install anything, because they'd rather prevent the catastrophic event that something's going to accidentally close on you, which gives the perception, and in software engineering, it's all about perception, actually, because reliability, I don't know how reliable software is. It's perception of it, and something that isn't even that reliable can be perceived as being more reliable, depending upon what part of it you actually notice crashing. Actually, you notice. If you know, let's say, for example, you were writing a term paper in Microsoft Word, and you know the file was up, but you didn't realize it wasn't saving. That might be a problem, actually, perception-wise, and you may not actually trust that word processor anymore. If you do that, you're not going to buy it again. If you do that, well, that's kind of what happened with WordPerfect. It would actually spontaneously close occasionally. Bad problem, bad user perception. Lo and behold, Microsoft Word outbeat it anyway. So, okay, so the user's perception of reliability. The personal computer that crashes frequently versus the machine that is out of service for days or 2 days straight. Most people would actually think that the one that crashed frequently was more reliable. Some people would actually say the opposite and say, well, it doesn't crash frequently, but it's not working for a couple of days. So if a website went down on you and it was something that you were using, let's say it was the ITU EMS or something, it went down for a couple of days, actually that's I think better than if you went in and in the one time you tried to post something it didn't work. As a user, you're going to, you know, that was one event, one time, the system was under maintenance and it didn't work for you. You're going to think the system's completely unreliable. So a database system that crashes frequently but comes back quickly with no loss of data, which is good, compared to a system that fails once in 3 years but the data has to be restored from a backup. That's kind of an issue. I would want the first one, maybe, no loss of data, maybe, but let it crash frequently. So, actually, people had issues with their cell phones initially. What if you lost your phone? What happened to your address book? What happens? So now we have techniques and we have things that make it more reliable. What's it really doing? It's giving the user a perception of reliability by backing things up, by making it available on a server so you can sync your phone. Now they actually copy everything on a SIM card or something, or they copy it on the memory card or something that's in the phone. Gives you the perception of more reliability. So a system that does not fail but has unpredictable periods when it runs very slowly. That's what we get with most internet applications, actually, when there's a high user bandwidth going on and the program's being accessed and used a lot. But, you know, it hasn't died, but it's running real slowly. So these are some of the things to think about when you're designing an application or a service or a product. And what it is basically adding value or taking away value from the perceived notion of a product, essentially. And it's all perception, if you think about it. So in Software Engineering 1, I talked about the metrics, and I talked about how to measure reliability, measure dependability. And I said it was a bunch of junk science, essentially, because it is to put a number on something and qualify something in terms of a standard makes no sense if you're just looking at one. And I said, you know, it's probably better to look at a couple different techniques and put them all together in sort of a packaged report to say that this software, because how do you really say that the software is 100% reliable, if you're going to say that, or 99.9% reliable? You have to have some way of proving that. Otherwise, the customer's going to come back to you and say, well, how do you know it's reliable? Well, because it doesn't make an error. Well, how do you know that? And then that's when you say, well, because we tested it. It's like, well, then how did you test it? And then lo and behold, you put the product out on the market, and 5 days later somebody does something you didn't expect that they would do with it, and all of a sudden it's now completely unreliable and worthless in the perception of the user, of the group that bought it. So we have traditional measures. We have, like, let's say, for example, the mean time between failures. We have availability, or the uptime. And we have the mean time to repair as kind of quantitative measures that we can kind of put on the software reliability. If the thing takes a long time to come back up after a failure, it's less reliable than if it comes up quickly. But then again, what we have is called protective software systems that correct themselves. So if it fails and then, let's say, it rebuilds a database or backs up something up or does something, and it takes longer for it to come back up, the user's perception is that it's not as reliable. But from a software engineering perspective, it's taking care of itself. It's repairing what caused it to fail or something. So there's that mystery. Oh, no, it's going away. It's going away. No, oh, no, it's back. No, it's going away. See, it'll just, no, it's going. It's gone now. No, it's going. It disappears. It goes and it comes when you least expect it, and then it goes away. So, I don't know. I think somebody out there with one of those little gun things, you know, like a real laser thing, you know. Actually, I shouldn't tell you this, but if you really want to irritate a teacher, get one of those little red pointer devices and start. Actually, I have one on this thing here. Start going like this with it. That irritates me. But I'm not looking at that, so it doesn't really bother me. So. All right, so the noise is gone, so I can continue. We have market measures. We can actually take and measure the reliability of the software based upon customer complaints. Not quite as reliable as sheer data, but sometimes customer complaints can tell us a lot more. Because this is how operating system companies actually fix themselves. Software developers, they go, oh, well, what's going on? So we go to technical support and we figure out how many people are calling in because their system keeps rebooting. Or what are they complaining about? This is slow, that is slow. Because we never see any of these problems when we're testing it ourselves. It's always the customers that are finding these problems, right? So that's actually kind of a measurement. If you can put something out on the market and get no complaints, then you know it's pretty reliable. And you can actually use that as evidence right there. Especially if people are using it. Now, if you put it up but nobody's using it, then there might actually be an issue with it, especially if it's a feature that they don't like or want. It's not really telling you about the reliability at that point. It's telling you about how popular the feature is. It may not be good at all. And then also comes customer retention. Hard to tell you in modern day development environments. If you build software over and over again and you have a good reputation as a developer, and you keep getting more customers, it's going to basically be a good sign that you're reliable. So a lot of people use these when someone says, yeah, how reliable is your program? And you can say, well, you know what? We only got 5 customers who complained about it within the last year. And we have a bunch of repeat customers. So that's actually probably a little bit more helpful to use as an assessment measurement versus how many times the thing has failed, because you may not actually even know that. And then you have customers or companies like Microsoft who wants to collect the data. So that's when they implemented that program in XP, I believe, that said, do you want to send a message to Microsoft every time something goes wrong with your computer? So there was a little option, you could send the message. What they were trying to do is collect data from the field, from customers, and actually use that to increase the reliability. And in some aspects, I think it actually helped, although it's kind of irritating. A lot of people don't want to send messages out. So now actually the same thing happens, you just don't get an option. It still gets sent out. In fact, websites do the same thing with logs and things. So sometimes you build a feature into the software from an engineering perspective just to ensure reliability. Maybe it's an optional report, a log file, or something that can help you troubleshoot the problem, given that you're expecting problems to happen. So those people who don't expect anything to go wrong at all don't even worry about reliability, essentially. They don't build anything into the software program as a feature to help them assess anything. So, okay, user perception is influenced by the distribution of failures. How often does something fail? How many people are affected? This is kind of like what happened with AT&T. Nobody. I don't know why AT&T is getting such a bad rap. So their network got slow. Well, they introduced a phone that was utilizing a lot of bandwidth, and they were the only ones who had it. They got everybody on it. So yeah, it's got to be slow. It's a lot faster now, but people still think it's slow. That's because half the people that thought it was slow moved off. Went to another carrier. Now it's actually pretty decent. So, it's the perception. It's influenced by mass media. It's also influenced by other factors. Once something has failed one time, it's no longer reliable in a lot of people's minds. So, hypothetical example might be cars that are less safe than airplanes in accidents per hour, but safer in accidents per mile, actually. And when you compare all of the high-profile plane crashes against all of the daily automobile accidents that occur, more people get injured in their cars than they do flying. But back, when we had a couple of airplane crashes back, a few years ago, now it's pretty safe to fly. But for a while, people were going, "Oh my God, it's not very safe to fly." But when you add the numbers up, you're not as safe in the car as you are. It was still back then safer to fly, even with plane crashes, than it was to drive a car. So, actually, driving an automobile is very dangerous to do. Actually, you know what they say? Walking is not as dangerous. But you always see pedestrians being hit, bicyclists being hit by cars constantly, especially in California. So, okay, so matrix reliability metrics for distributed systems. So these are systems that are on more than one computing environment, cross-platform, or cross-networked. Traditional metrics are hard to apply to multi-component systems. And this would be something, as an example, with cell phones on a cellular network, where we have one carrier, like let's say AT&T, and oh, good, it went away. Nope, I'm waiting for the sound to go away. I'm not quite sure what's causing it. Oh, it went away. Very good. See, it comes and goes. I don't know what the problem is. See, that's not very reliable. See, it's back. Maybe it's complaining about my comments about reliability. I don't know. Now, a system that works, in this particular case, only 70% of the time. This audio system work. But when it works, it's actually all right, I think. I don't know. All right, let me get back to this as I was, again, distracted. So multi-components working together, it's hard to assess what the problem is. It might be a connection between the components. It might be a factor of the component. As an example, you see this all the time with internet companies selling service to computer users. And let's say you have a Microsoft Vista system. It's going to run slower, regardless of what kind of network connectivity you have. Or you have an XP system or a 7 system. Or you have a bunch of computers that are configured differently that are all connected. You're going to get varying levels of different speeds that are delivered to each one of these locations. to say that one is slower than another, you have many different factors to consider. It's very hard to put a reliability kind of number on that. So what ends up happening is people, like an example, an ISP carrier is going to guarantee up to a certain amount. So you're going to get a range, essentially. So you can put a range on your software, too, which is how this 99.9% reliability comes into play. So when you're writing the spec up, you say, well, it has to work successfully a majority of the time, and then you quantify, well, what is the majority? 80% or 70%, or only 1 out of 20 transactions can fail. So you end up putting on, and it sounds like you're expecting problems to happen when you do this. But you put a range in there, and the range ensures that if you can meet that range, then you've met the requirements for the reliability. So in a big network, let's say, for example, you're given a moment, something will be giving trouble. At any one moment, something might be giving trouble. And there might be very few users that actually see it. Only 1 or 2 users might be affected by it. Or sometimes you end up with a lot of users that are affected by something. Generally, it might also be a time and occurrence kind of an event that occurs. So with network traffic, this is very common. In fact, people complain about this all the time with websites and shopping engines. Well, I tried to log in, but I could never purchase from the site. But other people purchase just fine. I'll say, well, what time were you logging in? What were you logging in from? So many different factors that might actually present a problem. And a system might have an excellent average reliability, may give terrible service at certain times to certain users as well. It might not necessarily just be everybody's affected, only 1 or 2 people. And there may also be components of the system administrators that, they rely on automatic reporting systems to identify problems that arise, and the automatic reporting systems don't do anything. This is when you get admins who rely upon logs and rely upon error reporting. So unless a user is particularly interested in keeping the program, rarely are you going to call up somebody and complain about the program. Instead, what you're going to do is take a look at the software that's running, complain about it, remove it from your computer and not use it. You're not going to be vested enough to actually send an email message. Well, some people do, but not every consumer is going to send an email message to the makers of that software and say, hey, you know what? It's really good, but every 5 transactions, the program closes. So what ends up happening is you have a lot of situations where problems existed, they've been around for years, and people have worked around the problem. Or people just select not to use the program because it has a particular problem. You see this all the time, actually, when you go into companies and everybody is supposed to be using a piece of software, or everybody is supposed to be, you know what, maybe it's this. Maybe it's this thing. Let it go, it'll go away. It'll go away. But this is wireless, and this is wireless. I think I figured out the problem. No. Watch this, watch this. Let's see. No? I don't know. It sounds like it's going to go away. All right, I took off my wireless device. Wow, now it's getting worse. It's like a tap dance. I didn't bring my tap dancing shoes today. All right, sorry, it's just extremely, what do you call it, irritating. Okay, thank you. All right, does that mean we don't have sound? Okay, that means I need to speak louder. Okay. Oh, no, we don't have the slides either. Okay, can we put the slides back? Actually, my computer doesn't have power anymore either. Just unplug that one. Yeah, there you go. There you go. Perfect. All right, sorry about that. This was definitely, okay, there we go. I'll fix it. It's going to come up any minute now. So. Yeah. It takes a few minutes. It's got to warm up, go through its little cycle thing. Okay, so what you're not looking at is a requirement specification for system reliability. Because remember when I originally started talking about reliability, I mentioned and said that it was part of something that we want to stick in the requirement specification. And, oh, there it is. It's warming up. There we go. And let's see if we can get this back on. Oh, there we go. All right, now we're back in business, sort of. At least we can see what I'm talking about. So as an example, let's say you have an ATM card reader, and you're putting this in a machine, and you know what, an ATM, it has to be reliable. And then the age-old question comes out where software engineers constantly, well, how reliable does it need to be? Because you think about it, you know, I'm just writing a little program for fun. Problem is, everything in the consumer's mind, whether it's a little applet, whether it's some utility that they'll never use, has to be reliable to a certain point. There's certain user expectations. So, and this is an example of how you would actually kind of figure out for an ATM card reader, what kind of reliability specification am I going to put in? So we can have different levels. And so we can say, because the thing is, when something fails, it fails for many different reasons. And there's different components, as I mentioned already. So we have the component of what happens when it fails, how often does it fail as a metric, how often does it take to recover once it fails, and how long is it down for, and you know, other different components that we can play that take a part into this. So we can come up with different failure classes. We can say, you know, it's a minor, it's a major, it's a medium, or we can specify out in this particular example by what happens. Example, permanent, non-corrupting class versus transient, non-corrupting, or corrupting. Obviously, we don't want any corrupting, so in the metric we have never. We never want it to corrupt data because that would be catastrophic. We'd rather have it not record any data and lose the data than corrupt data. So in our example here, in terms of taking a look at the last one here, the corrupting category, a pattern of transactions corrupts the database. It can't happen. Never. So in the middle, a system cannot read an undamaged card. Well, we're going to allow 1 in 1,000 transactions. So 1 out of 1,000 good cards that the user puts into the system, we're going to let it fail. And that's acceptable. Because the thing is, you can't have it, going back to that comment I made, it can never be 100% reliable. So you actually have to kind of step down a little bit, and as a software engineer, predict everything that's going to go wrong with the system, and figure out, well, what level of accepted, you know, how many things can go wrong, and it's still okay, it's still good. And then if it does go wrong, have a contingency plan for it within the software. So if the system fails to operate with any card, we'll reboot it, essentially. So this is kind of like what happens in terms of our operating systems. Okay, now that I don't have a mic, I actually have to talk louder, which means I have to talk over all you guys who are talking in the back. So don't talk so I can save my voice. Okay, thank you. All right, so if the system fails to operate with any card after a certain amount of time, go into a default mode, reboot yourself. So a lot of times we see devices that have this kind of logic built into it. So as an example, if it starts failing, it already knows that there's a problem. And then, you know, rather than having it manually fix itself, then the system itself knows how to do it. It's like self-repairing. A lot of operating systems have this built in. That's why we have safe mode. That's why we have rebooting and reorganizing, reverting to last good version of whatever. And that's how the ship ended up in that situation. In the beginning, I was talking about the ship that went off course because it was on autopilot, and the autopilot had some logic built into it that was kind of outdated because the GPS failed on it and went into auto mode. Well, it did what it was supposed to do, actually. Problem is, you know, what it did was outdated. What it did was inappropriate for the change in the system. So it costs money to actually put that default behavior into that GPS. And it costs money to actually record every time something goes wrong, to fix a problem, to reboot the system. Because it's time and energy that goes into that software engineering project that changes, that adds to the requirements, that puts in features like log files and stuff. So we have a cost-benefit analysis in terms of the percentage money-wise versus uptime, with the notion that you know, you'll need to spend more money on new functionality or improved reliability. And there's a big question mark going there with, it may not necessarily cost you more money. It might be a design issue. Or it might be something you can build into the design that doesn't cost you anything that makes your software more reliable. And your software needs to be reliable, otherwise no one's going to buy it. No one's going to use it. As I mentioned previously, reliability is a user perspective, is in the user's eyes. So it's like, what is it? Beauty is in the eye of the beholder, whatever. So software reliability is in the eye of the user and their perception of how reliable your system is. So nobody ever wants to put anything on their computer that's not reliable. It doesn't work. So that is a major issue. So central computing systems, as an example, what do they do? Central computer serves the entire organization. Any failure is serious. This happens in big companies. In fact, you see it when, oh, the computer systems are down. Ooh. Well, we have a centralized computer system, a client server, and the server goes down, which means all of the clients are down. Could be a problem. So we have things like mirrored servers, we have duplicate servers, all sorts of redundant things going on, backup servers. All we have is plan B, because you can never actually determine when the system's going to go down, and hopefully it won't go down. So step number one, you want to gather the data on every one of the failures. So this is pretty much a process to go through the diagnose to figure out, well, what should we do? Well, if you don't understand the problem, you can't fix it. So at the first point, you want to gather the data. So 10 years of data in a sample database, every failure analyzed, hardware, software, environment, human. Yes, you know, the environment, actually, in fact, this happens a lot out here when it gets hot. Not so much in California, but in other areas where the temperatures in the summertime get hot, or even the wintertime get too cold, and the environment's not good. You get condensation on electrical equipment, stuff. Things can fail due to weather conditions. So you gather all the data you can. In this particular example, they gathered it over 10 years. You may not necessarily be in business for 10 years. You know, you might have a fewer, and you might actually get it from different sources. They took the data from their hardware, software, and information collected. Step number two, to analyze the data. Take a look at it, weekly, monthly, annual statistics, numbers of failures and interruptions, mean time to repair something. Because sometimes also the decision on what to fix depends on how long it takes to repair something. And if you're trying to weigh the cost of how much you're going to spend on reliability versus the revenue you're getting from it, you're going to have more expenses if you have to hire people to fix something more and it takes them longer to do it. So if you can go on the time-consuming stuff, reduce that down, you can actually save the company a little bit of money in the end by focusing on the time-consuming, although maybe not as critical repair, but they're time-consuming. So that might actually be a decision point. You can graph the trends by components if you want to, or you can actually graph the trends by not only component, but other factors that might play a role. The failure rates for disk drives, maybe. Failure rates for power failures, maybe. Also crashes caused by software bugs in each one of the modules. Or you can actually graph it out by heat and weather conditions as well if you wanted to. It's part of the analysis. And the third step is invest some resources where the benefit will be maximized. So just because something is broken, it doesn't necessarily mean you need to fix it. It depends on how often it happens, how long it takes to fix it, and how expensive the fix is. So you could actually kind of weigh out everything and say, well, this one's cheaper than that one. We'll work on the cheaper fixes first. Or you could kind of work on the other way around and say, well, although it's not going to cost us very much, it's going to cost us more, let's say, to fix this one, but it's going to save us time and how often it gets repaired. But maybe it's a 3-hour job, but it only happens once a year. So you can't necessarily look at that factor either. Basically, the scenarios, you have to look at everything as a big picture. You can't just take one or two characteristics. You actually have to put it all together. Orderly shutdowns, let's say in terms of the investment in resources, you can actually create a process for the shutdowns after a failure, prioritize the order of the software improvements, software patches and things, change procedures for operators, maybe have them do things in a different order that prevents the problem from happening. And sometimes this is when technical support people tell you, oh, don't open that application first, open that other one first, and then open this one. It's like, wait a minute, I'm not going to do that for the rest of my computing history. But, it's a kind of temporary workaround or something that the operator can do, or replace the hardware or replace the software, depending upon what it is you're working with. Could be a reliable kind of way of looking at it in terms of an investment. And in building dependable systems, there's 3 kind of principles. So we all want to build a dependable system that is reliable, but we never do. So it's kind of contradictory. Although if we can try to build something that's 100% reliable, it's not going to work. But we can make attempts to actually meet that goal. So for software systems to be dependable, what does that actually mean? Well, each stage of the development must be done well. That means everything from the requirement spec until the delivery of the product. You could focus your efforts on having a solid development plan, which is what we basically went through with Software Engineering 1. Kind of looked at making each one of those steps and phases in the development process reliable, so we have predictable results that come out on the end. And then changes should be incorporated into the structure as carefully as the original system development was done. So actually paying attention to the maintenance, as we discussed in the first part of this Software Engineering 1, the longer you maintain the software, the more it deteriorates, the more it gets damaged, the harder it is to maintain in the future, and software wears out this way. It becomes less reliable, less dependable with each new change that occurs. So don't hire junior level programmers who don't know anything to hack at the software, because you're going to ruin it. It's going to decay faster than if you spend more time and energy and be real protective about what you're changing. Because what ends up happening, software will just get less reliable the more it is maintained. Testing and correction do not ensure quality. Just because you test something, just because you corrected a problem, then you test it again and it passed, doesn't necessarily mean that it didn't cause another problem. So being being really good at the quality measurements, being really good at the testing procedures that you're performing, doing some regression testing, performing a lot of different things. But depending upon the system but dependable systems are not possible without systematic testing. Actually, ongoing testing as well. Bank systems will do this. In fact, if you build an accounting system, software that a company is using, you're going to want to have like automatic audit types of reports, or you're going to want to have, like, it's a banking system or application, or maybe it's something having to do with mission critical data or very important data that needs to be accurate. You can actually do manual cross checks with the data, and if it's a matter of just accessing the database, you can run a query to see if this number matches this number. Sometimes the systems themselves have consistency checks as well, and reports that can print out how reliable is something to be true versus something else. Because they're saying, going back to that old phrase, garbage in, garbage out. Just because the system, just because you're putting good information into the system doesn't necessarily mean the system's not making a mistake. So, and that's what we're talking about today, is when the system goes wrong. So in terms of a modified waterfall model for changes, we can run back through the loops, and this should look familiar from Software Engineering 1, when we went from feasibility, requirements, hopefully this is pretty boring at this point, system design, program design, coding, testing, acceptance, operation and maintenance. We'll come back through the other way and go through the same process for all of the changes and actually update the documentation. If you do this, then you're building it, essentially you're going back and you're changing the original build instead of doing maintenance. Yes, it takes more work to go back and fit the feature into the requirements and go back through the system design and put the modification into the design and then put it through all of the different implementations all the way through to the end. But in the long run, you're doing less wear and tear on the software. You're getting more reliable software that comes out of it. But in order to do this, you're not going to be able to hire a junior level or an entry level person to hack at it. So it's kind of like when someone builds a house and a professional contractor comes out and builds the house, and then we get the handyman that comes in and makes the repairs and takes and cuts something out that was like a supportive beam or something, or does something that messes up the integrity of the structure, or fixes something the wrong way, causes another problem. So this is kind of like hiring the contractor to come back out again and forget about the handy people who aren't trained. So, not to say that junior programmers aren't good, but if you're trying to ensure reliability, and if reliability is your focus, you don't want to hire a junior anything. So it's just, it's a priority. So you have to pay a little bit more, and you're going to get someone who's going to know hopefully what they're doing, and not going to be making a bad change. So key factors for reliable software. And we have the organizational culture that expects quality. Because if you think about reliable software, that's a loaded description. What makes software reliable? It's perception. So we have to have a quality kind of culture that knows what they're getting. As an example, if you download an applet on your phone, it can actually fail just fine. It can actually not even work. Half the features, but maybe you like something about it, and you leave it on there. That's fine. Because the culture of somebody who would actually download an applet, use it, your expectation is lower. You're not really expecting huge quality program as if you went out and spent $99.99 on it. So sometimes it's the price. Oops. Sometimes it is the platform. Sometimes it's the application in general, the nature of the work that you're doing with it. And you can approach the software design and implementation that hides complexity. So if you might have a structural design, object-oriented programming, you might use something to basically take all of the important critical features, encapsulate them, and then modulize them so that all of the programs are using a set routine that's been tested that is reliable. Versus another environment where a programmer might be writing their own algorithm to do something, or relying upon their own ingenuity to make something work, which may or may not necessarily be something that would be desirable. So also looking at precise and unambiguous specifications when coming up with your requirement specification, coming up and doing your analysis, looking at making sure that there's no way to interpret it outside of the intended interpretation. Usually what ends up happening, and you see this not only with unreliable software, but you see this with other problems that occur, is when there's more than one right answer. There's one way of doing it, but then there's also another way of interpreting the requirement, another way of interpreting the specification to be, well, it can do this, and maybe it does this well. But it also does this and this, but, I don't know, is it supposed to do this? Because what ends up happening, and this is just a hidden factor this is a known factor, people use software for all sorts of different unintended reasons for why the software was created. As an example, even Excel as a good example. People like to keep numbers and totals and use Excel to do averages, sums, and all sorts of different things. And they might be using this for an accounting program or something. And the intended purpose may not necessarily be to act as an accounting program or to act as a sales lead, scheduler or something. So the customer might actually be using it for this particular purpose and expect it to be reliable. And it might actually make a critical error. Maybe it doesn't round correctly, and nobody ever thought that would actually be a problem. And the original design of the system was not to be an accurate rounding. It only rounded, let's say, to one decimal place or something. It didn't round everything out correctly. But then people are using it for this. And so then they're going to come back and say, well, this doesn't work. It's like, well, that's not what we intended to use it for. So that's like when you specify it out. Sometimes it's the expectation you're giving the customer when you deliver the product. And you can't just put a bunch of disclaimers on there because nobody will use it. Here's like QuickBooks, but we're not intending you to use this for a real business. Okay. Because it doesn't round everything correctly and it doesn't use the appropriate tax laws. Oh, okay. Well, what do you use it for? Well, because if you don't have anything else, it's better than nothing or something. So, I don't know. It's a different philosophy when it comes to that. And then use of software tools that restrict or detect errors, strongly typed languages, source code control systems, debuggers. This is where you get people coming up with all these different specs. Oh, it must be written in this language. Well, and you go, why does it need to be written in this language? Well, because this language is a strongly typed language. It does a bunch of type checking errors. So if the program compiles and it runs correctly, it has a higher reliability. let's say, for example. So in the old days, in fact, I think it's still in existence, but don't quote me on this, the Department of Defense used Ada a lot because it was accurate, it was safe, it had a high safety, high reliability, and I could do this with my little fingers like a quote, because that's what's the perception, but it was actually a known fact that the language, although hard to work with, you couldn't make serious errors with it. It actually produced programs that made proper calculations and things. So people will use specialized languages for specialized applications, and you can specify, there's a lot of uses of the word specify, you can actually state what language you want this program written in, and you want it written in this language because it produces high reliable results, high reliable program. So this is why people stick with databases like Oracle, reporting tools like Crystal Reports and stuff, because they don't do rounding errors. You don't want a report that comes out that rounds out to the closest million or something when every dollar matters. Or database programs that truncate data or that lose data or that don't have security built into it or something. So a lot of times the selection of the programming language, the selection of the database is done for reliability purposes. So also programming style. There are different styles that give you better reliability than others. Some things that are inherent in design. So styles that emphasize simplicity, readability, avoidance of dangerous constructs. Those allow you to break the rules and stuff. In fact, even different object-oriented programming languages give you different levels of reliability in terms of how many levels of inheritance. How many classes can you inherit it from, and what is required in terms of the design of the classes, the location of the classes, the configuration of the JVM, what kind of features, if you're running with a virtual environment that's going to run in terms of, like, let's say, for example, Java. One of the biggest selling points of Java is that it has security built into it. If you write a Java program that runs on a distributed network, you got a security manager, you got a distributed objects manager, you got bunch of features that are built in to the environment that will help you manage the security, manage the reliability. Because when we talk about reliability, that crosses over into security, maintenance, updating. Because if the program can't be updated, how reliable is it? If it's insecure, if it produces bad results, it's not reliable. So reliability is kind of like a blanket A that you give, like, it passed everything if it's reliable. So, all right, so programming style. Also, incremental validation, also an important concern in terms of key factors, because you can validate something once and then validate it again, and everything before it failed, but this passes. It's kind of like when you fix a problem. Beginner programmers do this all the time. It won't compile, so I changed everything. Now it compiles, but this doesn't work. Because instead of changing the logic of the program to fix the errors, they made it compile. So they played around with it to get it to compile. So you can incrementally validate it and ignore about everything else that you just broke in the process. Which companies actually do. They fix something and then they'll go back and regression test it to go back and see if everything else that they didn't touch still worked, which is why testing and validation through the process incrementally is important as well. So in terms of building dependable systems, we have this organizational culture concept. And good organizations create good systems, theoretically, which is why you study software engineering, which is why you have good company, development team environment. So acceptance of groups, style of work, meetings, preparation, support for juniors. That's why I said, if you have a strong program, you ruin it by hiring a bunch of junior programmers to come on out and basically ruin all the work everybody else did on it. Visibility, that's also an interesting kind of concept. Sometimes, you have a bunch of developers that sit around in the back room, but nobody actually sees them. Nobody communicates with them. They're kind of working on their own, on an island of their own, sort of. And their process, what they're doing isn't really known. It's just that they keep producing results. And then you wonder, well, what's going on? And then later, after the fact, you find out, oh, but look, the program crashes when this happens. But it probably could have been caught earlier in the development if people had been, introduced to what was going on and they were familiar with, and they were actually able to see the final result before the final result was available. This is how beta testing becomes very important, when you kind of take a look at it and go, well, if we could test it out before it's released and actually give it to users who are going to install it on their own operating systems or put it on their websites or something, then we might actually be able to catch bugs and problems with the program before the program is out, like to the mass media and out to the general public. So that was one of the efforts that originally started to kind of improve the quality of software and provide some. It wasn't a replacement for testing. There's a different purpose for that. When people do beta testing, it's usually for reliability, because they want to make sure that their testing environment doesn't include all of the different things that a user might actually do to it. And if the user's going to have a perception of reliability, then the thing's got to work. And how better to test it than to put it out and give it to the user to try it first. And then if it's free and it's not finished yet, it can make errors. It can collapse. It can crash, and it's okay, because then that stuff is fixed. And then they get the real copy and it works correctly. So the concept's actually pretty good. Let's see, completion of a task before moving to the next one, actually completing the task and not leaving it open, actually ensures reliability. This happens when people rush too much. When the source code is not actually written yet, but the documentation is completely done. And or the marketing people have it out, have the brochures printed, but we don't even know what features are going to be in the software yet. And then, there's a mismatch between what the marketing people are telling the consumers and what the consumers are getting. If you got something that didn't have something that you were expecting, the reliability measurement is completely downhill from there, from that point forward. So documentation, comments, and code.
What section 508?
Yeah. Say that one more time.
Section 508.
508.
Say that you don't need to use the mouse, but you have to operate on the keyboard.
What is section 508 from?
Any product which is coming out to the market.
From IEEE?
Sorry?
From what specification is that for?
So there is audit system, or there is an act in the United States, it says Surveys and Oxley Act. It says
yeah. What was your comment?
Now
I know what you're talking about.
Even the Dependable systems also cover section 508.
Oh, it's all, yeah. The Sarbanes Act. Of what, 2000 and something, 2010 or, no, 2005 maybe? 2006? The government's trying to, I think your point is that the government is trying to regulate the expectation of, and that actually comes back with, that particular act actually did and implemented audits on companies and to ensure consistency among how they were treating customers, how they were doing their accounting records. Also, accountability for different product features must work with certain things. And this goes back to government compliance from the old days, even from like ADA, American Disability Act. From you have to have access. So a mouse button. Well, you were talking about the mouse, I guess. You have to actually have it configured so you can switch the buttons. It's part of the act. It doesn't have to have a wheel, but it has to be compliant towards left and for right-hand users. The keyboard. Yeah. Yeah, no, you have a bunch of things. In fact, that's a good example because it's not mentioned in the slide set, but in a lot of ways the government of the particular country that you're producing the product for is going to put reliability expectations on you as well. So standardization companies. As an example, you're building a network interface card, or you're building something that works with a computer that's going to be an accessory to something, a mouse as an example. Then you have to meet the standards of the organization, such as IEEE or something that's providing you the interface connectivity, that is not only making certain things available in terms of protocols, but you have to conform to it in terms of compliance. Like, for example, in the United States, you can't actually put out a electric appliance that plugs into the wall that uses the wrong frequency or wrong amount of voltage. I'm not very into electricity, so it's voltage, I know that. But it has to regulate the voltage a certain way. It has to conform to some grounding standards in order to be sellable. So the government regulates in some ways, and I think that was your point that it was putting out, that kind of sets forth reliability standards. Reliability that makes things compatible, makes things safe for the consumer. Because safety, in terms of software, we never really think about safety, but safety is actually a characteristic of software. We always think when we think safety, we think hardware, and actually I kind of think about it, there is a lot of risk in terms of safety that we're exposed to. And they're constantly telling you that, the cell phones are bad for the brain or something. I don't know. Like, you hold the cell phone up to your head. In fact, I missed it, but there was something on the news last night about that. Like, it changes something in your brain, or I don't know. It causes radiation. Yeah. I think that's a myth, actually. But I wouldn't be, surprised if they came out with something that was real. And it probably does cause radiation, but it's probably such a low level that unless you're, I don't know. Maybe I should go back and TiVo that episode. I don't know. It was on the news last night.
You have N number of cell phones right around you.
Yeah.
And you have the tower and so on. So it's not you as a person, but your mother, your sister, and so everyone carries their own cell phones. So too much radiation.
Too much radiation. Huh. I haven't really thought about that.
It's not just one cell phone, right? So
yeah.
multiple cell phones you can use.
Oh, it's for households that have multiple cell phones. It causes an excessive level of radiation.
So right sitting in this room, you almost have everyone has a cell phone.
Yeah, that's true.
So 70-odd, 80-odd cell phones.
So you guys are all contributing to the radiation, the cumulative hazardous radiation that's occurring in the room due to the cell phone usage.
And that's the reason
it's not very safe, and that's why the audio is going in and out on our recording. It's because of all the cell phones in this room. If you think about it, though, it's kind of like this has been along in terms of in terms of consumer products. Even the use of cigarettes, has been known for years it causes cancer, but people still use it. So if the cell phone causes brain damage, do you think people are going to stop using it? I don't think so. So people are still going to talk on their phones. So. You might not live as long, but you'll be in a higher level of communication with your friends and family. So. All right, I guess that's enough on that one. Actually, when you talk about safety, you'll see safety in requirement specifications. And it's usually with safety critical items. As an example, smoke detectors that have they actually have computer chips in them, some of them do, that monitor levels not only for smoke but for carbon dioxide and stuff. And it changes, it's a small little component, little program that changes the color of something, makes it yellow, orange, red. And depending upon how safe the particular area is, particular piece, but there are pieces like, for example, indicators on fire extinguishers. Do you really want they're just starting to come out with these things that say how old is it? Should it be replaced? And you look at the light, and you see. And if it makes an error and you rely upon it, your house catches on fire, and you pick it up, it's green, it's ready to go, but it doesn't work. So it's your use of the product, and you relied upon a safety mechanism that was imposed using software, computer software, hardware, that failed. And then that would basically have a liability to it because of a lack of safety that's associated. And I always go back and say, how many people want to, develop software that works in a heart monitor, and then, what happens if it fails and reboots? The person wearing the monitor is probably going to die. So people actually have to think about whether or not they really want to work in that type of software development to begin with. And then once they've accepted that, having to work with safety requirements and testing, then it becomes mission critical for the project. So, okay, so completing a task before moving on and not leaving it half done also helps. In terms of building dependable systems, you want to reduce the complexity. I know this kind of seems like a oxymoron or reverse kind of what happens with software, because as we start building features, it becomes more and more complex through time. And the whole goal of development, going through a process, is to take something that's very complex and make it simple, theoretically. So the human mind can encompass only limited complexity, So if you break it down, make it into something that's comprehensible, simplicity, partitioning things out. So take the big picture, make it smaller, make sure each one of the smaller parts is reliable, that it conforms, that it's safe and meets all of these quality expectations. And then to think, the big picture is the accumulation of all the smaller parts. And so then you've got your big picture accomplished. If you take the big picture and try to say, how can we make this thing safe? It takes longer to solve the problem. It takes longer to fix the problem. So a simple system or subsystem is easier to get right than the complex one, which is that quote on the bottom of the line, if you can see that on the slide. So it's a lot easier to fix smaller problems than it is to fix the big picture. So, and that's how most people kind of focus in terms of, well, what's mission critical, what's important, and then fix that stuff first. Although, you're still gonna have dissatisfied customers if anything at all is broken, but you're never gonna get 100% reliability. So, okay, specifications for the client in terms of building dependable systems. So specifications are of no value if they do not meet the client's needs. So this is another kind of thing where people come out with all of this data, all these specifications. Look, it does this, and it does this, and it does this, and it does this, and the customer comes back and says, but it doesn't do that. That's what we asked you for. That's what we wanted it to do. Then you've got an unreliable system that doesn't work properly, even though it does everything except for what the customer actually wanted, which is why, going back to the concept of using a methodology from the first course, that's why you use the methodology. So you capture everything that the user wants, you put it into a requirement spec. You do your analysis, you create your design based upon what was asked for, and that improves the reliability, improves the satisfaction. So the client must also understand the review of the requirements and a specification in detail. That's a major fault that happens, is the client doesn't read, which is what ends up happening when you give them a 25, 30-page requirement spec and say, here you go, here's what you want. Nobody's going to sit down there and read it. In fact, nobody reads anything, especially when, you signed up for a consultancy contract. Are you going to read the 20 pages of legal garbage that you're given? Or are you just going to sign, oh yeah, I want a job, okay. You're going to sign it. Rental agreements, nobody reads those. Employment agreement, nobody reads anything. So the customer's not going to read it either. But then ultimately what ends up happening in software engineering is the customer's going to come back and they're not going to be happy, essentially. And so, or they're going to say the system's unreliable. So appropriate members of the client staff must review the relevant areas of the design. This is another interesting thing where you get a company that's been in business for a while. They send out one of the managers to go get an accounting system, but he's not an accountant. He's just a guy who's sent out to procure the system. So they go to you, the software developer who's building the system for them, and you show this guy everything, but he's the wrong guy. So if they actually sent people that worked with the system, that would be working with the system from the company out there, the reliability of what they're going to build is going to be higher if you're building it to the right audience. And if the guy who's making all of the, yeah, it's okay, we'll prove it, well, I have no idea what this thing does, but okay, it's good, then it's really garbage and it's kind of a waste of time. So from the client's perspective, and the client is never going to know this, as you as the development team, you're the one who's going to have to come back and request the appropriate person to show up. Because what ends up happening is, they'll send over the guy who's supposed to sign it, who's responsible, but he doesn't know anything. So, and that's where you actually look good, because you want, the appropriate person. So that actually makes the software development company look more reliable. It gives you more credibility, because you're just not accepting a blind, this guy knows nothing, he's just going to sign it kind of response. Okay, so acceptance tests must belong to the client as well. It's not used for software engineering company. Acceptance is used for the client. So if the client owns it and the client receives it, that's more reliable in their minds. Because again, going back to that same comment, reliability is in the eyes of the customer. So it's their acceptance testing. It's their bona fide, yes, it works. And we looked at it. If you hold on to it, they can't go back and look at it again and see exactly what it is. And it gives them a little bit more surety, gives them more faith. Because if you think about it, let's say you're Wells Fargo Bank and you hired the software engineering company to make a teller system for all of your tellers to use. Are you going to blindly, you're the manager who's in charge of this project, are you going to blindly accept that the system works properly? No, you're probably going to want to see the acceptance testing. You're going to see the validity of it. You want to have audit reports. You're going to have all this backup stuff that's really not part of the program, but it's there for your reliability in terms of what it is they're delivering to you. So we have a quality management process. And this is what lectures number 6B and C, I'm only going to cover A today, but the continuation of this gets into the quality of software development. A lot more than what we covered in software development, software engineering 1. This is basically quality processes and process management. So we have an assumption that good processes lead to good software. That's the assumption I've been giving you all along. And it's actually an assumption. Actually, we don't really know for sure. And how do we know what good processes are, actually? You know, if you talk to different software engineering companies, they have different methodologies, different processes. So the importance of routine and repeatable processes actually has merit. Even if it's the bad process that you're doing, but it's repeatable and it's a routine, it actually gets better because then you can make improvements to it. So you're never going to start out perfect. So if you start out close to perfect, then the next time around, you get a little closer to perfect and a little closer to perfect. And it's repeatable, hopefully, if it's routine. So standard terminology, requirements, specification, designing, using standard document templates. So all of your requirement specs look the same way. They might be wrong, but they all look the same way. You can make improvements across the board. Using software standards in terms of naming conventions, internal and external documentation, and then reporting procedures, having a process in place for bug tracking, for change requests. You would be surprised how many companies don't have these processes in place because they never expect anything to be wrong with the software. They always think it's going to work 100%. So they don't plan for the unknown. They don't plan for changes. They don't plan for bug fixes, anything. So, okay, the concept of change. And considering change as part of the software engineering process. Because change happens, and having a change management system. So the change management system takes a look and might actually organize the source code, might do version control. We talked about this in Software Engineering 1 in terms of change management. But building change management into the company, in terms of its process, the volume keeps changing. That's why I keep... It's weird. It goes up and down. So. All right, so I'm trying to regulate how much I talk, how loud I talk to that. Now I hear an echo. Okay, maybe it's just me. You hear an echo? Okay, it's my ears. It's no problem. I'm almost done. Okay, that's as far as I can say. Thank God. I'm almost done. Software engineering management and version control as a concept, tracking and changing requests and bug reports. And this is not a process of having a now it's gone. Having a standard form that you fill out. This is a process of actually having a process of taking whatever information you're getting as input, performing the processing on it, producing the output and the change requests, and actually having the change implemented. And then you can audit this system and say, well, how often are bug fixes implemented per user request for changes, and how is the system working? Because I'll tell you what happens, actually. The loudest customer ends up getting their bugs fixed first. So the guy who calls in 100 times because he doesn't like the color of the mouse cursor is going to get a new color of the mouse cursor before the other guy who can't print. You know, because, and it may not be the criticality of it, but maybe the guy who doesn't like the mouse cursor is Steve Jobs or something, you know. Maybe he's a big guy, I mean, a powerful guy. Or maybe he's just loud. He calls in every single day to see if his bug fix is correct, and then people just want to get rid of him. So people actually control the change, sometimes the change in the configuration management of how that process is working. It's kind of like the loudest voice at registration is going to get the registration process first. You know, the people who complain the most are going to get the ITU EMS logins first. You know, when really it should be all of the new students, right? Because they're the ones that don't have the login. All right, but enough said on that one. So procedures for changing requirements, actually following the procedures and not allowing violations to them. Procedures for changing specifications for designs and for other documentation as well. Regression testing, as I previously mentioned, and release control. Knowing when to actually put it out, when it's actually done. And it's not necessarily done after it's implemented. Because what ends up happening is people fix problems. It's done, it's changed, it's ready to go. But wait a minute, we haven't tested it yet. Oh, we'll test it while we're packaging it, while we're shipping it. It's already available to the public as a download off the website. But it hasn't been tested yet. Because there was no release manager, there was no person who signed off on it to say, yes, it's okay, you can release this now. So, and sometimes it's just a matter of having people in place to actually have a process, a known process. And we're actually really good about processes around here. There's processes for everything. And people complain, it's a bureaucracy. Yeah, or democracy. There's, you have to vote on something. Yeah, and you have to fill out a form, and you have to have somebody sign it, and you have to get approval for it. And people don't like it, but it's there for a reason, because over time it's proven to be very effective. And so people that, are in software development, they don't like bureaucracy, democracy. They don't like anything. They just like to do things because they like it, and they think it should be done differently. It's a popular, common perception. And it's usually smaller people, smaller companies. Because you don't have to be a big company to get in the software engineering business. In fact, all you need is a computer and some source code. And ta-da, you're in business. You can be one guy. And you're not going to have a form to sign off on stuff if you're one guy or one girl or whatever. So anyway, point taken. All right, so reviews. There must be a plan or a process for the plan to actually perform and to actually go through and make sure that you're meeting objectives, you're meeting certain standards that are set out. In terms of the process plan, the objective is to review the progress against the plan, the formal, the informal. It's actually one thing to create a plan, another thing to follow it, and another thing to actually follow up and review it to see if it was effective. Because what ends up happening in when you talk about bureaucracy, I say, yeah, it's good. Democratic bureaucracy, yeah. We all want a plan, we want forms, we want to sign up. Then we go overboard. And then people start doing stuff because it's required, and they need to do that. But it may not actually be effective. Like, you might be getting all this approval, and then it goes in the trash can because nobody looks at it. Or there might be a problem with it, and the system breaks down. Because the more people you involved, the more outside of the company, internal company, basically, the more people that are associated with this particular project, the more bureaucracy, the more the plan has a tendency to fail, essentially, long story short. So you have to adjust the plan, the schedule of the team, team assignments, who's working on what, functionality. And it's not build, okay, rush over the weekend and finish it. Hopefully it should be build, we're done, and it should go flowing easily. Most companies, they hire a bunch of people towards the end to push it out the door when you're wondering, well, what happened the last 6 months? Nothing. It's kind of actually, it's like students in schoolwork, actually. Nobody does anything until the last 2 weeks of the term, and then they go, oh, deadline. Oh, my God. The class is going to end. I better start doing my homework now. So then they wait, and then it ends up, oh, I can't do all this. I need an incomplete. And then, you know the story, because half the end here probably have incompletes in something. So, all right, the impact on quality in terms of a plan, obviously it's done to reduce problems and improve quality. Good quality systems usually result from plans that are demanding but realistic. Realism and being realistic is also another key factor. So good people like to be stretched and to work hard, but must not be pressed beyond their capabilities. It's impossible to finish an entire semester's worth of work in one night before the final exam, or to not attend the class at all and attend the final and expect to pass it. So expectations, realistic expectations, are sometimes something that that don't necessarily meet up properly. And also reviewing the design and the code, having regular desk checks, having outside people coming in to take a look at the quality, And what do we have in bold here? Design and code reviews are a fundamental part of good software development. Actually, they are. It's not a good idea to have one guru senior programmer who does everything and nobody ever looks at what he or she is doing because they're good. No matter how good you are, a second set of eyes is always needed to actually double check to see what you're missing, because that's what happens when, I mean, this is the classic, scenario when you have the programmer do the testing of his own code or her own code. Never finds any bugs at all. It works perfectly fine every time because they're always running it with the same input and they're always running through the same process because they know too much about how it's running. Never impartial. Bring in an outside team, instantly they'll find more bugs and more problems with it. And same thing with code review. They'll find bringing in an outside programmer, the program's written just fine. Why do we hire someone who comes in and takes a look at what this guy wrote? Because, they might find something, oh, look at that. Might not cause an error, but it might be bad code. Or it might have a path that doesn't go anywhere, that terminates, or an endless loop or something that goes on that the programmer's never going to see. So, in terms of the concept, colleagues review each other's work. It's not only a learning perspective from if you have junior and senior level programmers working together, it can provide a good learning platform, but it also provides that second set of eyes, even if they're the same level. And it can be applied to any stage in the development. It can be formal, it can be informal. So there's a lot of different ways to arrange that and have that done. So benefits of design and code reviews. Benefits as well, extra set of eyes, as I mentioned before, can spot mistakes, maybe suggest improvements, because it's different. Everyone sees everything differently. Colleagues share expertise. They help each other. In fact, that's one way of actually learning how to do things, is to watch somebody else and see what they're doing. And in the meantime, you might see something that they're not even seeing. So an occasional tidy loose ends, incompatible between components, maybe can be identified. So something like stating the obvious, like, oh, I thought this was supposed to run on this platform. And the programmer goes, what? Oh no, wait a minute, I forgot. They're forgetting something. So help scheduling, management control. Fundamental requirements, the senior members must show leadership. They actually have to be okay with the fact that somebody else looking at their code. And see it as a beneficial environment. Good reviews require good preparation. You just don't want to send somebody in to look at something and they have no idea what they're looking at. They're not even a programmer. They don't even know. That's a waste of time. Everybody must be helpful and not threatening. It's not like, we're not going to pay you if this other guy, it's not like an inspection. A lot of people think every time someone looks at your code, oh, you're inspecting it. Oh, you're just trying to see how good I am or something, I mean, no, really, you want to put out a reliable piece of software, so you want to make sure there's no errors in it. So. Okay, so the full version in terms of the review team. So review is structured, is a structured meeting with the following people. Hopefully you've got someone to moderate the whole situation, mediator. You got a scribe, some record keeping, some constructive manner, someone to take notes, developers, interested parties, outside experts. Outside experts are actually kind of interesting because they can add to a little bit of element to it, like stuff that you didn't see. Like, why doesn't your phone do this? Or, say, I didn't do anything. I used to stand in here. Why doesn't your application do that? Because they see a lot more, and then they might be potential users of the system. So they might be able to say, well, if you changed it so it worked with Oracle or something, then, I would actually use this thing. But right now, I'm never going to use this or something, So they might actually have a pretty interesting perspective, and the client as well. In terms of the program design, as an example, you can have a moderator or scribe, a developer. The design team might be the developer. So you don't want to bring one guy in and bring everybody in. Interested parties. People who created the design, maybe had the idea to begin with. People who worked on the requirements specification. Programmers who will implement the system in the future, perhaps. Outside experts and clients. So, in terms of the review process, and this is kind of a summary of what we're going to hit in a lot more detail in the next lecture, there has to be some sort of preparation for it. because you've got to have some criteria of what you're going to review, some expectation of what you want to get out of the review process as well, and some code listing, something that you're reviewing. So participants study the documentation in advance, hopefully, so they know what it is they're dealing with by concept. There's a meeting, usually. Hopefully there's a meeting. If there's no meeting, you're not really having any joint collaborative review at all. So the developers are going to, essentially the ones who are leading the review are going to meet together, go through the documentation, describe each one of the sections, encourage questions and participation, hopefully with the group members. Must allow plenty of time and be prepared to continue on another day as well. Because what ends up happening is as soon as these people, interested parties, start talking, they end up taking up a ton of time. And if you've only reviewed 1 hour, or you've only basically reserved 1 hour of your time or 1 day, it's never going to be enough time. So static and dynamic verification. And we are kind of hitting topics that we kind of looked at in Software Engineering 1, but I'm applying this towards reliability. So in terms of the concept of static verification, these are the techniques for verification that don't include the execution of the software. So we can actually do a lot of this, a lot of the code review, a lot of the verification without even touching any of the software. And this is what I would call the traceability, going back from design and going into requirements, and tracing back from features. And you can actually trace all the way back from the testing documentation all the way through the requirements to verify. And maybe manual, or might use computer tools, you can automate it. The dynamic verification is the testing that we're doing. So it's the software with the trial data, debugging, removing the errors that might exist. And here's where the review process kind of fits into place. Because again, you can make the mistake of having really great reviews, but it's not related to the static or the dynamic verification or any of the validation. But validation is a little easier than the verification in terms of what's going on at this stage. But the reviews could be carried out throughout the software development process. So you're reviewing the development activities, you're reviewing the deliverables out of each one of the stages, and you're reviewing the code, and you're reviewing the processes behind the creation. So it's kind of an accumulation of everything. So from the top of this little diagram, we've got arrows going down this way, and then we have arrows coming up this way, meaning that validation and verification should work alongside with the reviews. So we don't have one meeting at the very end, because if you wait until the very end, then you're pretty much done. And so what ends up happening is you can't go back and fix anything. You've done your review, and it's too late now. So if you start at the beginning and you have the review after the requirements, you can actually say, hey, wait, you guys left out half of what the user said, and you guys did. Then you can fix the requirements. So your verification, validation can come back. You can work iteratively through each one of the stages by revisiting and reviewing as you're going through. Yeah, it takes longer, but the more times you do this, the faster the team gets, and the fewer errors you actually discover, and the more routine the reviews and the verification and the validation actually work. Because what you want to do is kind of build it into the process, so it's not an afterthought. It doesn't happen at the very end. Last thing you want to do is basically have it at the very end, when it's too late. In terms of program inspections, formal program reviews, whose objective is to detect faults. This is from a source code implementation point of view, or from a code. So the code may be read, reviewed line by line. That's what I call desk checks. Kind of like have somebody look at it. 50 to 250 lines of code in a 2-hour meeting to go through it. Nobody really wants to do this, and nobody does this unless they are forced to do this. But when you do this, it actually raises the reliability. I mean, if the thing has to be perfect or close to perfect, this is a great way of making it more perfect, making it more reliable. Requires team commitment, requires people to be accepting of feedback. So effective that it is claimed that it can replace unit testing, actually. It actually does prove to be very effective. The only problem is you get people with egos, programmers that don't want to take the criticism, think that somebody else is not necessarily trained to their same level, don't want to share anything, don't want to explain anything, and they aren't really good communicators to begin with, so it poses many different problems. In terms of the inspection checklist, here's everything that can go wrong. So far I've been talking about everything that can actually go well to improve the quality. Here's some common errors and common problems, and you actually see this often. Data faults, so initialization constants, array bounds, character strings that go wrong, and using giving an input it didn't expect, output that does unpredictable. Control faults, conditions, loops, and things. And as a programmer, you can probably figure out this is a pretty good list of problems that could go wrong. Inputs being used, interface faults, storage management faults, exceptions that happen, unknown exceptions, possible errors, lack of exception handling. So these are some of the things that the desk checks and the inspection checks actually look for. You can make an entire chart and use it as a checklist. And if you kind of take the checklist and cross it against the code, you can actually kind of see where, oh, we left out exception handling. Oh, and it might be thinking, oh, it works perfectly. But what happens if an error happens right here? There's no exception handling. And in order to do that type of check, you actually have to be skilled in programming. So usually the inspections are done by colleagues of the same kind of academic level who know how to write, know how to program the source code. So you can also use statistical analysis tools to assess the complexity, also assess to see if there's problems, likelihood of there being problems. This goes back into complexity measurements, how many loops are there, how many control structures, how many variables are being used. That's going to give you different reliability measurements from a statistical point of view. These are automated tools. You feed it the source code, it comes back and says 98% reliable. You go, what? Where'd that come from? Because it's going to take you 1 hour to do this, 1 hour to do that. And this is where I say some of it's kind of junk science when you think about it, because how can you tell me it's 98% reliable? Because, and then you can kind of tweak the code to make it 100% reliable, but is it? There's other factors that play into that the automated testing tool is not looking at. So program analyzers, they scan the source code for possible faults and anomalies. You can actually kind of do that. You can check, you're working with a language that's not strongly typed. You can check to see if you're adding liked data types together, if you're producing results that make sense from a logic point of view. It can check control flow, data usage, interface faults, storage management, are we saving something? Unassigned pointers, unassigned variables, arithmetic expressions. So see if something actually makes sense for its application. And then in terms of the statistical tools as well, you can cross-reference tables, show every use of a variable, every use of a procedure, how many times are you calling a function, how many functions are called a lot, and how many are never called at all, things of that nature. Some statistical information about the flow. Path analysis, that's actually kind of good. Identifying all possible paths through the program and which paths are unreachable. Sometimes you write programs and you can never get to that, and why is the code there? But you're supposed to be able to get there, but nobody ever gets there because the logic of the program won't allow you to actually get there. So, failures and faults, by definition, and this is what I've been talking about in terms of the reliability measurements. It's basically finding these failures and faults. Failure, software doesn't deliver the service expected by the user. The fault is the bug. So it conforms, the programmer or design error whereby the delivery of the system doesn't conform to the specification. And these are actually commonly misused words. People say, it fails, it has a bug. Everybody says it has a bug. But it is a failure, or is it a fault? You can actually kind of come out with a different level of expectation as well. Or level of, it's a failure 1, it's a failure 2. Different degrees of failures and faults that might exist. So here's some actual examples of failures and faults. I'm not going to go through all this, but you can read through some of the examples. If you're not familiar with it, what most of you are, because as a student you probably have written a piece of source that had a bug, had a failure, that did something. So mathematical, as an example number A, mathematical function loops for every from rounding error. Well, whatever. Those are just some examples. Let's see. I think I only have a couple slides left here, so we are winding down, believe it or not. So in terms of the terminology, this is kind of a recap of some of the things I talked about already. Fault avoidance is the objective of creating a fault-free, bug-free program. Fault tolerance, basically, after the bug occurs, does the system still run? Does it crash completely? Do some things work, some things not work? Fault detection is the testing and the validation, making sure that we can actually detect the bug before the system is put into operation, hopefully. And this slide goes through definitions for fault avoidance. And this is basically what we've been talking about already. So software development process aims at developing zero-defect software. So to say something is 100% reliable with zero defects, I don't know. Don't ever say that because this is really not true. Just say 99.9% reliable. That's more accurate, actually. Using formal specifications, incremental design, customer input, constrained programming options, and static verification, as we've seen, statistical reporting, testing. It's always better to prevent defects than to remove them later, if you can prevent them. Example, the 4-color problem, or whatever. We also have the concept of defensive programming that this kind of leads into, and it's kind of a different methodology that's used to kind of, say everything's going to go wrong, so let's just prepare for it and program in defense. So if anything can go wrong, it's going to. So in our defensive, we create redundant code, we back it up, we test it, we check for modification, problems that have occurred after modifications, implicit assumptions that are tested explicitly, things like that, risk programming. So we basically want to avoid the problem, if we can defensively. In terms of error avoidance, so how can we avoid errors? Well, we don't use, if a programming language supports pointers, a lot of actual students don't want to use pointers because it causes problems. It can create a situation where some result is unpredictable. Not using things, and this kind of works. This error avoidance list here is kind of bad, actually, because it kind of works against good programming practice. Because a lot of people will avoid things if they're not sure about it, rather than going out and learning about it to be sure about it. As an example, recursion that's on this list, or interrupts, or pointers. Those are actually good programming techniques if the person knows how to use them correctly. So just to knock them out and say, well, I'm not going to use these because they're risky. You could actually build a better design by using pointers on something, or make something run faster by using pointers than something else. So or all the variables in certain circumstances, but should be used with discretion, as the comment on the bottom of the slide says. And here's some examples of defensive programming examples using a Boolean variable, not an integer for a Boolean. Actually, using the right data type is good. Putting in error checking, using the right control mechanisms. Actually learning what these features are is not a bad idea. Especially if you're going to run into a situation where you're going to want to use them. And then we have the concept of software maintenance that actually reduces problems if it's maintained correctly. So most production programmers are maintained by people other than the programmers who actually wrote the original program. So basically, some questions to ask yourself are what factors make a program easy for somebody else to maintain? So if you build the program initially so that it can be maintained by providing internal documentation, meaningful names on variables, structures that make sense, lack of spaghetti code, organize everything out correctly, then you end up in a situation where the code is easier to maintain. And if it's easier to maintain, then it's more reliable in the future because, as I mentioned before, the longer we maintain something, the worse it gets, it decays. So what factors make the program hard for somebody else to maintain? We want to make sure it's good. It is maintainable, per se. And in terms of fault tolerance, a good approach in summary is to look at failure detection, damage assessment. If this goes wrong, what are we going to do? Reboot the system. Or that goes wrong, we'll make a backup copy. So fault recovery and fault repair is also kind of a consideration. Keeping in mind that problems are going to happen, so it's a matter of detecting, essentially, and looking for them, expecting the problems. So in terms of basic techniques that are used after the error continue with the next transaction if possible. Otherwise, if it's a critical error, critical stage, stop. So that's why I like a lot of ATM programs. As soon as something goes wrong, it stops. It spits your card back out. Make sure to spit the card out. Don't deliver any money. Don't print out anything. Don't. Basically, it's kind of like backup plan. Timers, timeouts on the network connections, errors, corrected codes and data, keeping log files, error reporting, stuff like that is good. So, and the lo and behold backup. So, the backward recovery, being able to roll back out of a transaction, keeping save points in transactions. So having a system that has checkpoints. It says, well, if this has passed and this has passed and this has passed, okay, we can go further. Which is kind of like what the logic of most ATM machines do as well. I mean, you take your card in, okay, the card's readable. Password's good. Okay, password's readable. Okay, verify this information. Okay, we're good. And then it kind of goes through sequentially, step by step, until it's safe to do a withdrawal or safe to do a deposit or something. And the steps aren't really that much, if you think about it. But it does go through sequentially. If anything's wrong at all, it spits the card back out. So, I'm sorry, not good at this time. Try again later or something. Or this machine doesn't do this. Okay, no problem. Let's see. How much more of this do we have? Oh, not too much more. I just wanted to pump ahead to make sure. I am winding this down. Okay, so software engineering for real time, in terms of special considerations, special characteristics of real-time computing requires extra attention to good software engineering practices. When we talk about real-time systems, then we talk about harder to make it reliable. It's up all the time. It's relying upon current data that's being sent in. There's a lot more monitoring that happens, obviously, a lot more log files, a lot more let's capture the current event. And then there's a lot more focus on the recovery. So in terms of the requirements and specifications, development tools, modular design, so heroic programming will fail for real-time environments, essentially. So, testing and debugging needs and special tools for these environments. In fact, you have real-time debugging. If you have a real-time application that's running, you're going to have real-time debugging because it's not a static thing that just you load up and it just sits there. So the kind of troubleshooting and the kind of bugging that happens, it's more happening after you've delivered it. Because in a real-time system, if you deliver something, you have to actually, and this is the same thing true for non-real-time environments and just for static software applications that you run on your computer or anything that you're running software on. Once you deliver it, it becomes live. Once it's live, you have to be more reactive. You have to monitor a little bit more. So that's why people put together, technical support departments, capture the data, figure out what the bugs are, bug reporting tools. So testing and debugging becomes necessary. Debuggers cannot be used to test real-time performance, actually, because you don't know what's going to happen until it's implemented. So you don't know what happens, when the people in accounting go on and access their stuff in the middle of the day. Network speed might slow down. It might affect maybe the performance of something. You can simulate the environment. Might be needed to test interfaces, adjust clock speeds, do all sorts of different things to the program. But real-time computing poses a lot of, as well as distributed computing, poses a lot of challenges. So general purpose tools are not available in most cases because a lot of real-time environments are very specific and very proprietary type systems. So, some notable bugs. This is your last slide. Those of you who are getting antsy. Good people work around problems. The best people track them down and fix them. That's probably good food for thought to leave with. But these are some notable bugs. Actually, there's been a lot. There was like that math cap. When the Pentium, one of the Pentiums came out, there was that math coprocessor error. There have been, throughout history, there have been some interesting errors that you'd think, well, why didn't they catch that? But the problem is, unless you put it into place, unless you see the system work, you're never going to catch everything. So with that kept in mind, that's when you start looking through and working through some of these techniques to improve the quality, to improve the reliability. All right, so that was 6A. It was the first part of reliability. Next week, I think it's more on quality management, quality review process. But don't quote me on that. We have more in terms of safety, security to talk about in terms of software engineering. So we are done for today. Thanks for being quiet. And for putting up with all this strange noises. I know the volume keeps going up and down.
No, because the mic is...
Oh, the mic keeps moving? Was that what?